A very good afternoon and a warm welcome to the third session of the Professional Development Program organized by BMS School of Architecture in collaboration with Indian Institute of Architects, Karnataka Chapter. Today's session is titled Big Data and Cloud Collaboration in Architecture and Construction. And our speaker, Dr. Suryakanta Biswal, is a research fellow in the Department of Civil and Environmental Engineering, University of Surrey, England. He is currently working in structural health monitoring, a project funded by the Engineering and Physical Sciences Research Council. He has also worked as a research fellow in the BRNS DAE India's project titled Development of a Model for Evaluating Pre-Stress Losses Considering Creep and Shrinkage Losses in Concrete and Relaxation Losses in Steel over 100 years, from September 2012 to March 2015. The last 1 year, he has been working as a lecturer at SSN College of Engineering in Chennai. He has had many years of experience in scientific program, mainly with MATLAB, and commercial software for finite element analysis, mainly ANSYS and Abacus. Thank you so much, Dr. Suryakanta, for accepting our invitation. And now the platform is all yours. Please take over. Thank you so much.
Thank you so much, Shreya. So it's my pleasure to present something what I do on my research. So I'll be talking on, so my main background is civil engineering. So I work on health monitoring. So, but the techniques, they can be used on any application on any actions. So let me share my screen. So I hope you can see my screen.
Yes, sir, it's visible.
So today I'll be talking on the big data and cloud collaboration, but mainly in the health monitoring of bridges. But as I mentioned, the action, here I'm talking about the health monitoring, but the action can be anything. So there are so many actions and the application. So today I'll be talking on the bridges, but you can apply to any other structures also. So the actions I was talking about, it could be design optimization, it could be construction schedule optimization, it could be life cycle assessment, it could be risk mitigation, it could be project planning, it could be post-construction. So post-construction can be health monitoring or something else. The post-construction can be the, here what we do with health monitoring, it can be life cycle assessment, it can be repair, it can be rehabilitation, so many things. So these are the actions. So today I'll be talking only on the health monitoring. So the next is applications. So I'll be talking on the bridges, but you can apply the same techniques to buildings, wind turbines, dams, any kind of structure. So today's outline. So first I'll start with big data, especially in bridges, whatever type of data we get. Then cloud storage, why you need cloud storage for the bridges. Then little bit I'll talk about the maybe more I'll talk about the health monitoring of bridges because that's my expertise. Then I'll talk how we use the big data and cloud and we interfere all the techniques to identify the condition of bridges. So the big data in bridges, so the data can be mainly it comes from sensors. So the sensor can be physically wired sensor or it can be wireless sensors. So physical wired sensor, we attach the sensor. It can be strain gauge, accelerometer, LVDT, temperature sensor, any kind of sensor, but they are wired. So the wiring will be connected to a local sensor network. So the sensor network will then be connected to a local server. So the server will be very close to the bridge site. So it could be, so if the bridge is close to a railway station, so maybe the server will be at a railway station or maybe at some remote location. So the next is the wireless sensor network. So there's no wired connection. So the wireless transmitter will transmit the signal. So if the number of sensors, so each sensor will transmit the signal and it will be received by the central server. And then there's another is hybrid sensor network. So we'll have the physical wired sensors, but those physical sensors will be connected to the base station so can you hear me?
Yes, sir, you're audible.
Okay. Yeah. Sorry, I thought I lost the connection.
No, sir.
So the physical sensors, they will be connected to the base station, and the base station will be connected to like from the base station, all the data will be transmitted to the central server. Yeah, so the data will be transmitted to the central server. So all the data will be stored in the central server. So the cloud storage, in the cloud storage, so there are two options. Either you have physical drives to store the data at the central server, or you have a cloud storage. You have those storage at some remote location where you can access the data, all the data remotely. So from the local server, all the data will be transmitted to the cloud storage, and from the cloud storage, the center server, like the asset engineer, the asset management engineer, or anyone who wants to access the data. So the engineers will be here at the center server, so they can access the data from the cloud storage. So instead of getting the data from the hard drives, they can remotely access the data from the cloud storage. So here I'll be talking about the health monitoring part. The third part is health monitoring. So yeah, so in health monitoring, there are many aspects. So one major aspect in health monitoring is the damage identification. So we have done a lot of research on damage identification. So here is a case study of damage identification in a concrete bridge. So we cast lab scale models of the bridge girder. So these are concrete girder, reinforced concrete girder. So in the concrete girder, there could be damage due to loss of sections due to corrosion, due to loss of bond between the concrete and steel. There could be loss of stiffness of the member. So we introduced different kinds of damage in the lab. Then we took measurements. We use LVDT, strain gauges, accelerometers with different sensors. We did static test, we did frequency test. Then we did a FE model. So from the FE model, we divided the sections into multiple regions, and in each region we estimated, we run an optimization algorithm to identify the damage in each section. So if the damage is here, the optimization algorithm will tell that at a section here there is damage. It will also tell what is the amount of damage or what is the quantification of the damage. So that was a concrete structure. This is a steel structure. It's a portal frame. So it could be from an industrial building. So this is a representative structure. So here we were interested in monitoring the loss in the bolt tension, the pre-tension in the bolts. So that means if you lose the pre-tension, the stiffness of the connection will change. So based on the change the stiffness of the connection, how the response changes. So similarly, we did an FE. From the FE, initially we saw it doesn't match the result. Then we did a model for the damping. So the nonlinear damping, that's very critical if you're using the time-based and damage identification. So we did a nonlinear damping model, and based on the damping model, you can see the model accurately predicts the responses from the structure. So it can identify the damage, it can identify also, so like once you have the calibrated model, you can also predict any response that you want for a given types of loading. So then this is a case study for the damage. This is mainly for the quantification because we knew there's a damage. So if it's not visible here, but there's a hole somewhere here, and it's like some 30 centimeter long. But the thing is, it was corroded all along the length of the bridge. So this is a wrought iron section. So the damage here is the delamination. So we went to the site, we put sensors there, accelerometers. We did a model testing. Then we did a full scale model. And from the full scale model, we could identify the damage, mainly the quantify the damage. So next is a case study for this one. So this bridge, I think this is a Stockwood bridge. So these are called jack arch bridges. So in these kind of bridges, so you have the steel girders, but the steel girder will be sandwiched with jack arches. So the arches are masonry arches. The purpose is to prevent corrosion, to prevent the exposure of the metal to water, so that there won't be any corrosion. But there was a big accident in 2009 in Scotland. So since you cannot see what is going on inside, you can only see at the bottom. One of the sections was heavily corroded and the bridge failed. So it was a catastrophic damage, failure. So this is a project by the railway department here in the UK. So they wanted to identify, or they want to know if you can identify the damage only when the exposure is available at the bottom surface. So you can have, you can see only the bottom part. You cannot see any other part of the steel girder. So the traditional damage detection technique, what they use, or the asset engineer they use, is they dig a hole near the steel section and they see. So physically they will create holes. When they create holes, that means they're introducing damage. So they wanted to avoid this technique. So they want to go for some NDT through which they can identify damage without damaging the structure in the way. So before going to the site, we did a lab study. So we cast half of the section. So it has the half of the wave and the bottom surface. And the wave is sandwiched with two material, first with wood, then with concrete. And we took measurement only on the bottom surface of the steel section. So from that measurement, we showed that we could identify the damage, even if it is sandwiched between concrete or wood. So it was promising. So the next task was to go to the site, but due to COVID, it was not allowed. So we were waiting till the time when we could visit the site to take the measurement and verify the techniques. So another application of health monitoring is the remaining life estimation. So if you know the outer sections of outer, like the dome shaped section in the nuclear reactor, they are made of precious concrete, post-tension concrete, and they have a service life of 50 years. So after 50 years, so this is a project funded by the BRNS. So they wanted to know the remaining life after 50 years, whether they need to add new tendons, or there are some extra dots available, so they could introduce new tendons and add more strength, or whether the strength is sufficient, so they don't need to do anything else. So we cast post-tension concrete beams and slab. We kept them inside the humidity chamber under controlled humidity and temperature for 3 years. And like every 3 months, we used to take them out and take the measurement. And from the measurement, we built a FE model and numerical model. From the numerical model, we predicted the life at 50 years and beyond. So the next is how to infer all the techniques, the big data, cloud collaboration, and health monitoring techniques for the monitoring of the bridges. So here you said like you can choose in a locality or in a route from one end to other. There could be a lot of bridges, similarly constructed bridges. Sorry. So if you then what you do, you put sensors on the bridges and take the measurement. So the measurement will be stored in the local server. You can transmit the data to the cloud storage. So you keep on monitoring the data. So you have the data for all the, since these are continuously monitoring, they have huge number of data. So you transfer the data to the local storage, the cloud storage. So you have the data for all the bridges. Now, what to do with the data? So the central server will use health monitoring techniques for implement the health monitoring techniques for each individual bridges. Then the result or the outcome of all the process will be stored as outcome given data. So the data given this bridge and the outcome given that bridge will be stored, and each set of data will then be used in a machine learning framework. So a numerical model will be created based on the input data and output data for a given bridge, so, and for a whole number of bridges. And this numerical model that is trained based on the data will be used to predict the responses or the damage in other bridges, similarly constructed bridges. So based on the trained data, we can identify damage, classify damage, or identify the remaining life of the bridge that we want to estimate. So here I'll show a case study. So the case study is Administrative bridge. So here the case study is to identify the remaining life of under bridges, the steel under bridges in the route from Bristol to Weymouth. So in this route, there are some 25 number of 20 or 26 number of steel under bridges, similarly constructed around 1890, so some 130 years old. So to identify the remaining life, we have the codal provisions. What the codal says, the codal provisions are mainly made for the cast iron, the steel, the structural steel. But these bridges were made of wrought iron, so there is no codal provision. There are some techniques to modify. There are some modification factors, but I mean, they don't have much trust in those modifications, so they gave us the piece. So they wanted us to experimentally identify the remaining life of the piece and create a digital twin model based on the machine learning techniques. So that digital twin model will include the data and the health monitoring techniques. And those, based on the digital twin model, we want to estimate the remaining life in all other bridges. So this bridge is the Yelahanka bridge. So it's close to the Yelahanka railway station. So over the Regal River, this is a single span bridge. It is 10.5 meter long. It was replaced in March 2020 with a composite steel concrete bridge. So after removing the bridge, they transported the bridge to our lab for identify or to experimentally determine the remaining life of the bridge. So the digital twin model that I was talking about will be consisting of the physical structure, the bridge here, the Yelahanka bridge, then the data. So here the data can be the geometric details from the drawings or from the measurement of the thickness using any NDT or laser scanning. It could also be the material details from the assessment report. So here in the UK, they keep the assessment report. So if they have a way to monitor the condition of the bridges. So if the bridge condition is well and good, so they do the assessment every 10 years. But if there's some changes, some visual changes, they reduce it to 5 years or less. So we have the assessment report available for almost 20-30 years. Then we can do some coupon test, some local test, some coupon test to measure the material properties. Also, we can do some NDT to measure the local or the material properties. Then we can do tests. So these are the experimental tests. So it can be in-service testing while the bridge is still in operation. It could be field testing after removing the base, and it could be model testing. Model testing means you have to use something like impact hammer to measure the model parameters of the bridge. Then, so these are the global behavior. Then you can also measure the local behavior using lab testing, like the coupon test or something like that. Then with the fatigue parameter test. So this could be a small section of the bridge, or it could be the full bridge itself. Then we'll have the global and the local FE model. So the global model, FE model, will be calibrated based on the global behavior or the responses obtained from the global measurement, and the local FE model will be calibrated from the local behavior, the local test, local measurement. So all these will include in the digital twin. And this digital twin, so this is a data inferred physical physics-based model. So this will be used to identify the remaining life of all other bridges in the route, in that route. So this is the in-service testing that we did. So before removing the bridge, so we went to the site and we took some measures. So this is a video gauge-based measurement. This is a contactless measurement. So we had targets. So we had a video camera somewhere here. As the train passes, it will deflect. We measure the deflection of the bridges, the main girder and the cross girder under the train load. So the bridge had 2 main girders, 7 cross girders. So we had so many of sensors, the LVDT and the position of the sensors. Then it was transported to our lab. Then we did a full-scale load testing, the static load testing. So when it came, it had the deck, bridge deck, the timber deck. So we did the testing on the when the timber deck was still there, and after also removing the deck, we again did the static testing. So we had all this sensor. We had mainly 30 LVDTs to measure the displacement, and we had 40 strain gauges to measure the strains. Then we did the model testing. So the bridge was hanged by a crane. Then we put sensors. Then we had impact hammer. We did the model testing of the bridge. Then the next, so the previous slides I showed focused on the global behavior of the bridge. So now to estimate the local behavior, we cut the bridge into number of sections. So here the main aim was to identify the damage at the connection. So the fatigue damage at the connection. So we had to load at the center of the bridge and look at the damages or the number of cycles at which there are some visible damage at the connections. So we had full cross girder and we had a small length of the main girder. That's mainly because the machine, to apply the load, it has some clearance between the columns of the machine. So it cannot be more than 80 centimeter at one length to go inside the machine. So we had 80 centimeter at one end, the other end was little bit more because we could afford to have a little longer. So one end we had 80 centimeter, or the other end we had 1.2 meter long. So the next was to identify the parameters. So the parameters means the material properties of the bridge was given in the assessment report, also in the code, the network rail asset management code. So we did the global FE model, including the timber without or removing the timber also. We had all the components of the bridge, including the stiffness, L stiffness, T stiffness, the rectangular stiffness, angles, everything, except the rivets. So we did not include the rivets in the global FE model. And to get the train load, so we got the train load from the database. So in the database, from given the route, you can identify or you can determine the type of train that moves on the bridge or over the bridge, and from that, from the class of the train, then you can identify the type of load that comes onto the bridge. So we apply the same load in the fatigue machine, in the fatigue test, also in the static test. So this is This is a sample of the prediction. The prediction is the blue one, and the measured response is the red one. So they match pretty accurately. So, but there were some difficulties because the bridge, then we identify there are some out of plane behavior, so mainly due to the imperfection. So instead of only the vertical, getting the vertical response, we also got some horizontal responses that we included in the FE model, in the calibrated FE model as a part of imperfection. Then we had the laser scanning to get the actual shape of the members. Then the local model includes all the rivets also. So it includes each and every component that is available in the piece. Then the digital twin will have the global local substructure model. So it will have the global FE. It will also have local part. So if we are interested in this, at this connection, we'll have the local section here. If you want the behavior at here, so we'll remove or we'll shift the local connection to here. So this is the framework, the final framework, how we use the all the tools to identify the or to monitor the bridges in the route from Bristol to Weymouth. So we have, let's say, 26 number of bridges, bridge 1 to bridge N. So we keep on monitoring the data and those data. So then some wireless sensors are attached to the bridges. So those data will be stored in the cloud, and in the center server, we'll have the asset engineers or the health monitoring engineers. So they will create a FE model or a structure twin for each bridge. So the structure twin will be calibrated based on the measurement. Let's say we have the measurement for bridge 1. So the structure twin of bridge 1 will be calibrated based on the measurement on the bridge 1, but we don't have. So we have the full measurement, means the global, local, everything on bridge 1, but we have only the global measurement on bridge 2 to bridge N. So the calibrated or the structure twin of bridge 1 will then be modified so that it matches, so the responses from the bridges matches with the responses we measured from the global response we measure from bridge 2 to bridge N. So these are done in center server. So for each model, we'll simulate the structure for each response, then identify damage. So now if we want to measure or we want to estimate the damage in bridge, let's say bridge N. So we'll have the measurement trend. So we have a measurement trend. This measurement trend has a lot of sensor on it. So this trend will pass on the bridge. So let's say we want to estimate or monitor bridge N. So the measurement trend will pass on bridge N. So then we'll identify damage based on outlier. So if like from the structure twin, we have some responses from the FE model. Now we have measurement on bridge N. So if there is a change in response, and based on the changes, we can create damage identifiers, and based on those damage identifiers, we can use machine learning algorithm to classify damage, whether level 0, very small, minor, moderate, severe, or extreme. And once we identify damage, then we'll calibrate the structure twin, and it will go to the center server, and this data will again be fed to the cloud storage. So this is the full structure of how cloud data and big data is used in the monitoring of the bridges. Thank you so much.
Thank you, Dr. Suryakanta. We have a question for you, if we can take that.
Yes, yeah, so.
So, Harinath, sir, you will be unmuted. I mean, you will be given the permission to talk. If you could unmute yourself and ask the question. Thank you.
It's a simple question for me. Is how this the local data, what we use from the experiments,
yeah,
that can be updated in the global model. That's because the local data is always cannot match with the global data, right? But that's definitely in the using the global FE model. So the calibration is the how you use those things.
Okay, so here the local model is this one. So we have the local model. So the local model have the one cross girder and two small section of the main girder. Okay, so what we do here is we put sensors, lot of sensors. We put the load here. Then we measure the responses on the cross girder, on main girder, or the connections. So based on the FE model, we then match the responses from the FE to the measurement. And here the parameter, then we look for the parameters, the updating parameter that we could use to update the FE model. So the parameters could be the friction coefficient between the member. So between the angle here and the web of the cross girder. So what's the friction? And also the stiffness in the normal direction. The other parameter which is usually used is the material stiffness or the Young's modulus of the material. So we identify the parameters, then we find the possible ranges, maybe from the experiment or maybe from the literature. So using the possible ranges, we run an optimization algorithm to identify the parameter, the optimal parameter for which the measured responses match closely to the simulated responses. Once the local model is calibrated, then that local model will be replaced in the global FE model. So this is called a global local substructure model. So this will include the local model, all the small components of the local model, and also it will also have the global behavior of the global model.
For example, if we wanted to know the life of the structure, because you are also doing the fatigue of this, right?
Yeah.
Those parameters, how that will help to find out the life of the structure?
Okay, so what I understood is how the fatigue parameters
are identifying the extent of damage for the present structure.
Okay, yeah. So there are few models. So like the network rail code, the CIB 025 code, it has a model. So based on the current damage condition or the fatigue parameter, so how many number of cycles has crossed till now, and what is the stress range. So based on those parameter, it has a way of saying whether the current condition is moderate, severe, or minor, or there's no damage. And it will also has a model to tell after 10 year or 20 year what could be the damage based on the current damage condition.
Oh, okay. So that means we are also tells the service life of the bridge.
Yes. Yeah. So but the issue is that model was meant for structural steel, not for wrought iron. Oh. So our aim or the main objective of the project by the network rail is to update those numerical model they have.
Yes. And questions. So generalizing this, basically we are doing, and you are doing at one particular structure or one particular bridge. So yeah. Generalizing this to basically you're using a numerical model to all other bridges, right?
Yeah.
Yes. How reliable these things when it coming to the real-time data when we are measuring at the real-time structures? Is it closely matching the results and one bridge to other bridges, or how that?
Yeah. So we have done testing on 3 bridges. So from the prediction from our FE, the prediction matches like the current bridge, the difference is around 20 to 25%. The Mortlake station bridge, the response matching was up to 5 or 6%. That was very close. So what we have learned is if you can model the bridge as accurately as possible. So I have seen that the prediction matches very closely. Not if not very closely means it's 20 to 30%. That 20 to 30% is very close in terms of or in words of the asset engineers. They will be happy if the match is around 40% or even a little more than that. So for them, 20 to 30% is extremely well. And that was our the highest difference or the largest difference. The smallest we got around 5 to 6%.
Okay. And thank you. Those engineers is going to monitor continuously here onwards as a kind of, or they will according to
yeah, the aim was to tell the engineers whether they need to monitor or not. So from till now we have the 40 test specimen we are running now. We have run for something like 4 million cycles on that. That's like 100 years of chain load on the bridge. So the life of the bridge is already 130 years. It was designed for 100 years. 130 years has already passed, and it can take more than 100 years without a single damage on it. So these bridges are not prone to fatigue. So there could be some other kind of damage like corrosion or something else, but they are not sensitive to fatigue damage.
Yeah, thank you. It's a very nice presentation. Thank you.
Thank you so much, sir.
Thank you so much, Dr. Harinada and Dr. Suryakanta for giving us a very detailed explanation of your work. We understand that there were connectivity issues, but you still stayed with us, so we are very grateful for that. Thank you so much for being with us today.
Thank you so much for the opportunity. Thank you.
Right. Thank you so much, Dr. Suryakanta.
Yeah, bye.